Welcome back to Further Solutions Academy. Further Solutions Academy. Encourage us more to share our video anywhere you see it. Subscribe. If you have not subscribed before, kindly press your subscribe button for direct updates. And also, any video you watch from us, you try to leave your comments from updates. Okay. If you want to book for our online class, you can reach us, or you can comment below, or you reach us with this line. You can book for online. You can call us and WhatsApp us, and also Telegram is allowed, either of the three. Okay, on this video, I'll be walking you through examples of topology, or example of topology. Sorry for that, example on topology. Now, the outline of this video, the first one I'm talking about examples of topology, and the second one will be I will use the example to explain discrete and indiscrete topology. By the end of this video, you understand all this. You understand it by all this. Now, let me start from. I think by now you know how to define topology, and I've been telling you this is our third video on topology, and in the first video we explain definition towards sets and sets and definition of topology. Now on this video, just examples of topology. But before I give example, let me remind you definition of topology. Now look at okay. This is definition of topology. Don't forget, I've been on this I was explaining this in the last video. Take note of that very, very well. These are the three axioms that tells us that such a set is a what? It's topology set. Now, let me quickly read. Let S be a set. Let S be a set A topology T, which is we call it tau. Mostly we call this T tau. Tau on S is a collection of subset of S, each on open set such that number one, empty and the set given is a member of what? Topology. Two, the intersection of finite many sets in T are also in topology. Three, the union of any collection set is in topology. Please, this is just tau. We call it tau, and that is topology I'm talking about. These three axioms are very, very important when we talk about topology. Before you conclude that a given set is a topology, you must to test for these three axioms. And before let me quickly introduce what I want to explain earlier. Now, when we have something here, when you have the set and the empty, we always call it trivial or indiscrete topology. Trivial, or we call it trivial. I think by the end of the video you understand that, and the transition and other part of it. Now, with this what I've explained here, this can also be called trivial. If you have something like this, it's the smallest in topology sense. Now, let me explain this with example so that you can understand what I am trying to explain. Now, if I have this type of sets, okay, look at this question. Determine all the possible topologies on X. Now, this is the set on X. That is very, very important. By now, I've explained what is called subsets, and I've explained, I think you should know all these things from our first video. Now, when you have something like this, how do I go? Listen very well. It's very, very simple. The first thing you need to do is that, don't forget that when we talk about topology itself, which is tau, we always use collection of subsets of X. Collection of subsets of X. That is what is called topology. And what I mean by that, this is my X from the question. We have only two elements in X. don't forget, if I want to do this, cardinality or the number on a given set, we can call it n of s cardinality, which is equals to what? 2. Now, it means my n equals to 2. And if I want to get the numbers in a given set, I will use a formula which is from our secondary school, 2 raised to power n. When my n is 2, which is going to be 2, it means 4. It means subset of this particular set should be 4. Now, it should be 4. Now, it means I can say that the subset of x, which I can say that what? It can also become topology. Let me quickly choose. Also implies topology, which it will be equals to empty, the given set, and singleton set, and yes, they are all. Can you see 1, 2, 3, 4? That is what I mean by 4. That is the total number on a given set. Since I have this, I can now say that, let me check for the answer. The first one, number 1, empty, and the given set are in tau. The empty and the given set and the subset, which is subset is the tau, which that is number 1. Number 2, can we move on to the second one? The intersection, the empty intersection of the given set is also equals to what? This is equals to it will be equals to this intersection, this, it will be equals to the set itself. Empty intersection this, it will be empty, which empty is an element of what? Tau. That is what you need to know. This intersection, this, it will be what? Empty. That empty is in that tau, which is, it means that is number 2. Number 3, if you also move this intersection, this, can you see another one? If I have set A intersection set B is also empty. You can see empty is in what? Is in tau. That is very, very important. And if I even have set A intersection the given set, it will be equals to what? It will be equals to A himself, which is singleton set, which also is in what? Is in tau. Can you see all this? That is tell us that what? That's O's. It means assume 2 O's. Now that's O's. Number 3, I will now move on to the union. Empty union the given set, it will be equals to the given set. Please take note of that. And the given set is an element of this, which is element of what? Tau. It means, since I have something like this, since I have this, I will now say then is a topological space or on X. Topological space on X. Now, or another one, or I can say that T, which is tau, is a topology on X. Anyone you will feel like saying. Now, since I test for those things and I have them, this is what I mean by what? Topological space. Now, the smallest note something, not this very given information, note the smallest topology is, okay, you can ever collect, can ever get called encryptive topology. Topology. Or you can call it trivia, or you call it, you can also call trivia topology. Please take note of that. I think I've used this opportunity to explain what is called indiscrete topology. Now, can you see this, the same thing as this? Now, when you talk about trivial topology, it means is the least collection you can ever collect in a given set. Normally, mostly is always most time, all time is two elements. Let me use the word elements. Now, this is an example of trivial or indiscrete topology. It means if my tau is like this, empty, and the given set. Now, that is the least I can ever collect from this given set. It means is a what? Is a trivial topology. Now, before I continue, let's quickly explain what is called I've explained trivia, which is indiscrete topology. Let me use this opportunity to explain what is called okay. I've used the opportunity to explain discrete topology. Note, okay, now before I continue, that is what is called indiscrete topology or trivial topology. It means is the list of the topology, which is the empty and the given set. Now, before I continue, okay, let me generate another one before I continue from this given question, because I've generated first one. That is the first one. The second one I can also talk about is that if I have another topology, another solution, I've done one. This is solution 2. Now, if I have my tau as empty and the given set and one of the set. Now, look at this. The first thing I need to know is that number one, you know that this and x are elements in what? In tau. Very, very important. The number two you need to know, if I have empty intersection x intersection the given set is equals to what? Empty, which is also element of tau. Can you understand? Is there already? Empty is there. And the last one is the union. Let's take the union of. Okay, before I continue, which is number 2, look at this. X intersection A is a set, which is an element of tau. Is there already? Now let me move on to the third one, which is the union. Now, if I have this union x, it will be equals to x, and x is an element of tau. And also, if I have a union x, is also is equals to x, and also is an element of tau. Since I have something like this, it's also a what? This is also a topology. It means tau S is a topology. On tau. That is all. Now let me generate another one so that for better understanding, let me cite one more example on this part before I end this section. Now it means I'll call it solution 3 of this given set, which is solution 3. I've done 1, I've done 2. Now look at this. If I have my tau as I have empty, I have S, and I have B. Now look at this. Look at this. How do I know that? It's also a topology. forget it's also a topology. This is also a topology without looking at it. The first thing you need to know, empty and the given set, which is X, and in what? Tau, which is very correct. 2, the intersection, empty intersection S equals to what? Empty is also an element of tau. And also, if I have given set, which is B, distinguishing set, union S is also the same thing as what? S. It's also in tau. Now, it's also a tau topology. Now, all these things, that is what how to know that maybe something is topology or not topology. Now, let me quickly use this opportunity to explain what is called discrete topology. Discrete topology is also known as subsets in hex. Please take note of that. Discrete topology also known as subsets of given set. Now, it means subset of X is also the same thing as, is also called what? Discrete topology. Please take note of this information very well. I think with this I've explained discrete and indiscrete topology. I've told you that discrete topology is a collection of all the what, or the subsets, while indiscrete topology is the smallest set that you can generate from the what, from the given set, which I've explained that I think if I'm going to talk about discrete set on this given set I have above, it means this discrete set will be equals to, take note of this very well, I have empty, I have given set, I have A, I have B, and I have AB. It means since I have this, this is a discrete set. Is it discrete? Please take note of this very well. Now, why indiscrete is just like we are having the empty and the given set. This is empty and the given set. This is called indiscrete. Indiscrete. Please take note of that. Can you see discrete and indiscrete? I don't need to speak much English. I think I've shown you definition on discrete set. Now, before I continue, okay, now let me try to show one or two. Okay, before I continue, I would like to show another example that will tell us that a given set is not a what? It's not a set topology on it. The given set is not a topology on that set. Now, look at this particular problem. Look at this question. X equals to A, B, C, which is these are the elements on S, and the subset, the tau is empty, given set, and A, which is singleton set, and another singleton set, which is B. Now, how do I know that this is a topology or not topology? Let's check. The first thing I need to know, this and S are in tau. Very correct. 2, A intersection B. What is A intersection B? Is empty, which is in tau. And what else can I need to check there? What of A? A intersection B, yes, is empty. And what else did I need to know there? What of the singleton set with intersecting the given set? What will I have? I will have only A, which is A. I will have only A, which is also in in hertz. That is very correct. The last one, which is the C part. Now I want to check the union. Now let me have the union of that set. A union B, which is equals to what? A B. Not in tau. This is not in tau. And can you see, since this statement contradicts the axiom, this statement contradicts the axiom, it means I will now conclude by saying not a topological space. That is all. Not a topological space. Can you see in some cases that there is not a topological space? Before I end this video, let me show one. Okay, in my next video, I would like to give more examples on topological space, which is I will be talking about 3 sets or more, if possible. Don't forget you are home with further solutions academy. Once again, share, subscribe, and comment. Thanks for watching.